Welcome to the Space Telescope Public Lecture Series. Tonight, how Yavin IV and orbital mechanics destroyed the Death Star, from Mia Bovill of Texas Christian University. I'm Dr. Frank Summers, and as always, I want to welcome you to our presentation tonight and thank our amazing tech team, Thomas Marufu and Grant Justice, who take care of recording this and getting it out to YouTube. For our upcoming talks, next month we have a kind of special one. The Webb Space Telescope will be releasing their very first images on July 12th. That's 1 week from today at 10:30 a.m. Eastern Daylight Time. And on August 2nd, we will have Alex Lockwood from the Space Telescope Science Institute discussing those images in her talk titled Webb's First Look, Images and Spectra from NASA's Newest Great Observatory. In September, Guido Roberts Borsani from the University of California at Los Angeles will talk about very early happenings in the very early universe, first light, unveiling the properties of galaxies at cosmic dawn. And in October, we're going to have another very interesting and very special talk for you. It's called The Universe of Dante Alighieri. And the speaker is a retired astronomer from Italy named Spirello de Sorreggi Alighieri, a descendant of the original Dante Alighieri. And he will go through Dante's work and talk about his use of astronomy and the universal symbols that he used in his work. You want to know more about when these lectures, you can go to our website, www.stsci.edu/public-lectures. On that, you will find links to our webcasts, as well as a way to subscribe to our emails. Just enter your email address and push that subscribe button. You will find lists of upcoming lectures. And when you click on one of these lectures, you will get all of the details, including the speaker, the description, and after it has been recorded, links to the Space Telescope webcast and the webcast as it is on YouTube. As I said, you can sign up for our email list on our website. You can also subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, all one word. You will get new notices of new videos and reminders of live events like this. And if you have questions or comments, other questions for the speaker that you didn't get to ask during the talk, you can send them to publiclecture@stsci.edu. Our social media accounts, we have social media accounts for the Hubble Space Telescope, for the Webb Space Telescope, and for the Space Telescope Science Institute on Facebook, Twitter, YouTube, and Instagram. I myself, as I always say, do a tiny amount of social media. You can find me on Facebook and Twitter as Dr. Frank Summers. News for the universe, from the universe for July 2022. Our story tonight is about compact groups of galaxies. Now, when you think of a galaxy, you probably think of an isolated galaxy like this. This is the Sombrero Galaxy, and it's just a gorgeous galaxy here. This is got a broad disk and a huge bulge from this. We call this a lenticular galaxy. And people think of galaxies existing on their own. But galaxies don't always exist on their own. Sometimes you can find them in pairs. So for example, this is NGC 2207 and IC 2163. I'm actually not sure which is which, but these are two galaxies that are nearby each other in the universe. They're sort of one is passing in front of the other. These galaxies are not interacting yet, but they are close. And actually, when I think of galaxy pairs, I generally think of galaxies that have interacted, such as these. This is the mice galaxies, okay? Two galaxies that have come past each other, and they pulled out these big, long tidal tails from each other. You can see their cores, and they're probably going to merge together and form a galaxy. The other clumping of galaxies that we tend to talk about are clusters of galaxies. And so this is the Perseus cluster of galaxies from the Sloan Digital Sky Survey. And you can see there are dozens to hundreds of galaxies here in this cluster. And when we talk about clusters, we often talk about these huge clusters like Abell 1689, where the mass is so concentrated that general relativity comes in, and the mass warps the space. All right. And when you look through that warped space, you see lots of stretched out galaxies. You see what's called gravitational lensing. Abell 1689 is a really good example. And here are all these stretched arcs. These are galaxies on the far side of the cluster whose light has gotten stretched out while passing through that cluster. All right. So we think of individual galaxies, we think of pairs of galaxies, we think of clusters of galaxies. But there's another scale of galaxies that doesn't get as much play, but it's kind of important for us. Why? Because we live in a group of galaxies. All right. This is an artist's depiction of the local group of galaxies, which, as you can see, has our Milky Way galaxy in it, and has about 36 other galaxies. It's not a really big group of galaxies. Okay. It's only got 3 big size galaxies. Okay, so it's got the Milky Way, which is a large galaxy. It's got Andromeda, which is a slightly larger galaxy. And then it's got the Triangulum galaxy, also known as M33, which is sort of a medium-sized galaxy. Everything else in the 36 galaxies in our local group are all small galaxies. And so it's not really the most photogenic of when it comes to groups of galaxies. Actually, it's impossibly photogenic because we're in the Milky Way galaxy. We can't get out to get this picture, so that's why we have to rely on artist's drawing of it. If you want to take a really beautiful group of galaxies, one of the most famous that people know is this one, which is Stephan's Quintet. Quintet having 5 galaxies. You can see that this central one here is actually 2 galaxies merging together. But Stephan's Quintet is also not really a quintet, because this galaxy here in the foreground, this blue one, is actually not part of a group. Okay, it happens just to be projected along the line of sight. It's about 1/3 the distance of the other 4 galaxies in it. Okay, so there are these groups of galaxies, and for Hubble's 32nd anniversary, we had another really beautiful photogenic group of galaxies called Hickson's Compact Group 40. Paul Hickson, was an astronomer who became fascinated with these groups, and particularly the groups that appeared very compact on the sky. Because the thing is, if galaxies are this compact, if they're physically that close together, well, then they're going to merge together, they're going to interact, and they're going to basically, become one individual galaxy eventually. What we call the dynamical time, the time it takes for them to merge and mix together, isn't that long compared to the age of the universe. So finding a lot of these compact groups, Paul found over 100 of these groups of galaxies, sort of tells us something about how things are going in the universe. And so you can see that there are interactions going on in this, okay? So if you look at this central galaxy here, okay, the spiral arms are pulled out just a little bit and stretched out. And if you look at the one here on the upper left, it's kind of hard to see because the gas is all dark in it, but there is a tidal arm, its spiral arm that's been pulled out, really stretched out on that. So you can see there have been interactions. And the interesting thing about this group is that it's a very compact group, because if you look at the size of the elliptical galaxy here, the stretching from the top left to the bottom right is about 2.5 times that. Okay, so if these galaxies were all at the exact same distance, they'd be merging together. So really, what's going on here is they all are, unlike Stephan's Quintet, there are no foreground galaxies here. They're all pretty much the same, but they have to be sort of stretched out along the line of sight. So it's like we're looking down a pipe of galaxies. And in order to get that idea across in our press release, Well, we made a video. So this is a zoom into and fly through, a 3D fly through of Hickson's compact group 40. And that was our happy anniversary present to the Hubble Space Telescope for its 32nd anniversary back in April. So our speaker tonight is Mia Bovill from Texas Christian University. Mia got her PhD from the University of Maryland here in Maryland, where I am. And then she did a postdoc down in Santiago, Chile, where she did some wonderful research down there, and then came up to us here at the Space Telescope Science Institute here in Baltimore and joined us for a few years. And then we lost her and she went off to Texas Christian University, where she is now an assistant professor. Her research is, as you might guess, not into Star Wars. She does not get paid to do Star Wars. She does that on her own time. If you remember, a few years ago, she gave a talk on Star Trek. So she is definitely a sci-fi geek. And she tells me that one of her favorite hobbies is playing with her cat named Minerva, which should also tell you that she's a bit of a Harry Potter geek as well. But her actual research, when she's not doing sci-fi or playing with her cat, is on the formation and fate of the first stars and galaxies. And as she said, as we were prepping for this, she is unbelievably excited for their new results from Webb next month. So, ladies and gentlemen, Dr. Mia Bovill.
All right. Hello, rebels, imperialists, and the occasional Botham spy. I'm going to be talking to you about how Yavin IV and orbital mechanics destroyed the Death Star, which is also a lovely gateway to talk to you about all of the phenomenal things that we've discovered about exoplanets since George Lucas released the first episode of his magnum opus. Before we go on, all images in this talk that are recognizable from Star Wars are, of course, the property of Disney, and they are being used in this public lecture for educational purposes under the fair use. So a long time ago in a galaxy far, far, wait a minute. The speed of light is constant. In fact, the speed of light is the speed limit of the universe. So nothing can go faster than light. This means that when we look out into the universe, we are actually looking back in time. It takes light about 8.5 minutes to get from the sun to the earth. So when we look up at the sun, and please don't look directly at the sun without proper equipment, you're actually looking at the sun as it was 8.5 minutes ago. This means that if the sun were to wink out of existence, we'd have 8.5 minutes of complete and utter blissful ignorance before we found out about it. And this means that the nearest stars in our galaxy, we are seeing as they were for Alpha Centauri 4 years ago. Betelgeuse, if everyone remembers, we thought it might go supernova. It's 600 light years away. So Betelgeuse might have actually already blown up the light from that explosion just hasn't reached us yet. And this turns astronomy into a time machine. The further out we look, the further back in time we look. The image on the left is that of the Andromeda Galaxy, 2.5 million light years away. And we see the Andromeda Galaxy as it was 2.5 million light years ago. Now, the good news is that because galaxies evolve over billions and billions of years, seeing a galaxy as it was a few million years ago isn't that big of a deal. But the image to the right is the Hubble Ultra Deep Field. And until the amazing things that I know were going to come out of JWST, this was one of the deepest images ever taken. Every point of light in this image is not a star, it is a galaxy. And some of these galaxies are 10 billion light years away. That means that when we're looking at the galaxies in this image, we are seeing them as they were only about 300 billion years after the Big Bang. So what does this have to do with Star Wars? Well, if far, far away, over long, long ago, is about equal to the speed of light, that means that if we had a powerful enough telescope, we could actually look at the galaxy in which Star Wars is happening and literally watch the Millennium Falcon doing the Kessel Run. However, I hate to tell you that JWST is actually not even powerful enough to do this, and we will have to wait many more years for far, far more powerful telescopes before we could do this. So now back to Yavin IV and the Death Star. So we've all seen this image. This is the rebel base at Yavin IV. The actual site where they did this is the Mayan city of Tikal in Guatemala. The Mayans actually are phenomenal archaeoastronomers, some of the best in the ancient world. They had nearly figured out the orbit of Venus, but that is a topic for another talk and another time. But in this image, we actually see some things that are very important to figuring out what the Yavin system is actually like and where Yavin IV and the gas giant that's orbiting are located in the system. For starters, you see all this green. There is life there. There is complex life, where you have complex life, you very likely have water. You also have these lovely buildings, which are clearly built by some ancient civilization that potentially grew up on this moon, which means that the climate and the orbit of this moon was stable enough over millions and millions, potentially even billions of years to allow this civilization and complex life to evolve. And if our rebel turns around, you see that they are not wearing any kind of an oxygen mask or breathing apparatus, which means that the atmosphere of this moon is an oxygen nitrogen atmosphere. So what does all of this tell us? Well, we have a rebel base, but more importantly, we have a jungle and an oxygen nitrogen atmosphere. And to have oxygen, specifically O2, you need to have life. The O2 spectral line that you can see here for a super Earth and for an Earth is one of the most important spectral lines that we can detect in an exoplanet atmosphere. If we see a strong O2 line in an exoplanet atmosphere, that is a very, very strong indicator that there is life on that world. And to have life, you need some form of liquid. You need some form of relatively innocuous substance in liquid form. And the most common, the best of these is, of course, water. So you need liquid water. Which brings us to the habitable zone, or you might have also heard of this called the Goldilocks zone. So you have a star at the center of a solar system, and that is the heat source for the entire solar system. If there is no other source of heat that doesn't effectively come from the main star. If you were too close to the star, the water will be in a gaseous state, and it actually will eventually dissociate and evaporate off of the surface of the planets, leaving a dry, barren world like Mercury. And actually, Venus, despite its very thick atmosphere, is also very dry. If you were too far out, you were too cold and the water freezes and you end up with ice worlds. things that we see, Europa, Ganymede, all the outer planets are ice worlds. And if you're just right, it's just warm enough that the water doesn't freeze, but you're cool enough that it doesn't form a gas. And this is the Goldilocks zone, or the habitable zone. It's the area around a star where liquid water can exist. And as the luminosity of a star increases, so the total energy output of a star increases, the habitable zone will move further and further out from the star. And something that you might notice here when we look at the habitable zone for our sun is that Mars is actually just inside the outer edge of the habitable zone for our sun. And what happened to Mars is, again, a topic for another talk and another time. So what kind of star is Yavin IV and Yavin prime orbiting? It's more likely than not that they're actually orbiting a relatively sun-like star. And the reason that we know this is because M dwarfs like Gliese 581 are extremely active. They shoot giant flares off of their surfaces. And when they shoot these giant flares off of their surfaces, they will hit and irradiate planets in their habitable zone. Because remember, their Goldilocks zone is much closer to their star than out where about 1 AU where our sun's is. And so it would be potentially very difficult or very challenging for life to arise, for complex life to arise on a planet around an M dwarf. But as we're going to sort of see when we really start talking about the exoplanets that we found, we've learned to never say never when it comes to the systems of our solar system. So what do we actually know about the color of Yavin prime? So one of the images that is, I think, probably one of the most famous images of Star Wars is the one that I opened this talk with, which is the scrappy rebel fleet going into battle against the Death Star under the backdrop of the bright red gas giant. But would a gas giant orbiting around a star in the habitable zone actually be red? And this comes, and it's red because of a combination of the types of chemicals in its atmosphere, the types of molecules in its atmosphere, and how those molecules are interacting with the radiation from the star. And a beautiful example of this is from our own solar system. This is a spectacular image, actually, of the aurora on Jupiter taken by NASA's Juno spacecraft. And one of the most things that we all know about Jupiter are these beautiful bands of color. You see the white clouds, then we have the red bands, you have some sort of beige up here. We all know about the Great Red Spot that first seen by Galileo Galilei in the early part of the 1600s. And what we're actually seeing when we see the different colors of Jupiter is that at these different points, we are seeing different depths into the cloud deck. So the Great Red Spot is a point where we're seeing all the way down into the ammonium hydrosulfide that is reflecting back red light. So we have to know about what would the atmospheres of an exoplanet in the habitable zone likely be made of, and how would that interact with light at the habitable zone. And this is, I'd like to really acknowledge Tad Komacek at Maryland. He is a world expert in exoplanet atmospheres and helped me out a lot with the answer to this question, which actually we don't really know yet. This is work from looking at colors of hot Jupiters and how they would look to the human eye. So these are not in the habitable zone. These are massive Jupiter-sized gas giants, or even more massive than Jupiter, that are orbiting inside the orbit of Mercury. In fact, the atmospheres of some of these would be so hot that their atmospheres would be made of metals. So this is magnesium, for instance. And while a few of these are red, overwhelmingly, they would not look red to the eye. And I emailed Dr. Komacek and I asked him, what did he think was likely for the color of a planet in the habitable zone? And the likely color of a gas giant in the habitable zone, he said, would be hazy, a yellow-orange haze. similar to Titan, which you see here, or Saturn. So unfortunately, Yavin Prime likely wouldn't be red. It would actually be more yellow-orangey like Titan. Second, what's the size of Yavin Prime? How big is the gas giant? And I promise you, because to figure out how orbital dynamics helped us, how orbital dynamics and the laws of orbital mechanics helped give the rebels just enough time to blow up the Death Star, we need to learn something about the gas giant that Yavin IV is orbiting. And to do that, we need to actually learn something about the size of Yavin IV. So we're going to make the first of many assumptions over the course of this talk. And that is that since all the rebels on Yavin IV are walking around without too much trouble, we're going to assume that the gravity on Yavin IV is very similar to gravity on an Earth-like planet. And the acceleration due to gravity on the surface of a planet depends on just two things: how massive the planet is and how big the planet is. A more massive planet of the same size will have a stronger acceleration due to gravity. You would weigh more on that planet. But if you take a planet with the same mass and you make it bigger, the acceleration due to gravity would drop and you would weigh less on that planet. So a good shorthand for this is that the acceleration due to gravity depends on the density of a planet. So if two planets likely have the same density, they will have the same acceleration due to gravity and the same mass and the same size. So what you're looking at here is a subset of all of the planets that we have found using various methods, but largely with the Kepler spacecraft. Coming across the bottom is the planetary mass in Earth units. So 1 here is 1 Earth, 10 Earths, and 100 Earths. And notice that this isn't a linear scale. This is a log scale, which astronomers actually use because we deal with huge ranges in numbers. Vertically, you're looking at the size of the planet. So this is 1 Earth diameter versus 10 Earth diameters. And one thing to notice is that all the terrestrial planets that we are finding tend to have about the same density as the Earth and Venus. And since we already said that Yavin Prime and Yavin IV formed in the habitable zone around their world, which is about 1 AU out, we can assume that Yavin IV is made up of basically the same stuff as the Earth. So the size of Yavin, and we also know that it probably has the same surface gravity, which means that it is about the same size. So we now know that each of these circles is about the size of the Earth. So how can we use this to figure out the size of the gas giant? Well, I could have done this using complicated geometry, angles, and some very terrifying calculus, but instead I drew circles in PowerPoint. So the big red circle is roughly the scale of Yavin Prime. And then the green circle here represents the scale of Yavin IV, the moon on which the rebel base is occupied. And the diameter, and then I just looked to see how many Yavin IVs fit across Yavin Prime. Nothing fancy, nothing up my sleeves. And the diameter of Yavin Prime is about 8.5 times the diameter of Yavin IV, which is about, and since we're assuming that Yavin IV is about the size of the Earth, that means that we have a gas giant that's about 8.5 times the diameter of the Earth. And this is actually in line with the size of the gas giants in our own solar system. Jupiter is a little over 10 times the radius of the Earth. Uranus and Neptune are more like about 6 times the radius of the Earth. So this is actually in line with that, what that ratio would be in our solar system. However, as a moon, Ganymede, the largest moon of Jupiter, is 26 times bigger than Ganymede. So whereas the Earth-Moon system The Earth is actually only 4 times bigger than the moon, and our moon is very big compared to the Earth, actually bizarrely so. So what we can say is that the size of Yavin Prime, of the gas giant, is in line with what we expect for gas giants, even if Yavin IV is on the big side for a moon orbiting a planet of that size. And when we compare this to what we know about not only our own solar system, but exoplanetary systems, planetary systems orbiting other stars, you see this red bar coming across here. And so this is roughly equivalent to something the size of Neptune or Uranus, or maybe even Saturn, but not Jupiter, and not these super Jupiters, these super massive hot Jupiters that were initially discovered orbiting very, very close to their parent stars. So, and I want to remind you of something. George Lucas wrote these in the 1970s. Star Wars Episode 4 premiered in 1979. Actually, for those, I'm about to make a chunk of you feel very old. That was several years before I was born. But it was also 16 years before the discovery of 51 Pegasi b, the first extrasolar planet. So George Lucas it was 16 years before we've even discovered any planets in other systems. And so far, he's doing pretty good. So how do we determine the mass of Yavin IV and what you all came for? How does orbital mechanics explain the destruction of the Death Star? So basically, so Yavin IV is nicely orbiting at the gas giant, and the Death Star pops out of hyperspace. And why it pops out of hyperspace on the other side of the planet, how you get something the size of a moon moving through hyperspace, talk to George Lucas on that one. But the important thing is that that's not a moon, that's a space station. And that's the crux of this. Is probably, again, one of the most famous lines in Episode 4 is, that's not a moon, that's a space station. The Death Star is effectively an orbiting body. Once it enters a system, that means that it's not going to be able to just fire thrusters and move around. Once it's in the system, it's going to have to obey the laws of orbital mechanics and go into orbit around either the sun of that system or around, in this case, the gas giant. So the Death Star has tracked the Millennium Falcon, it comes out of hyperspace, it goes into orbit around Yavin Prime, and now it's got to wait to orbit around the planet until the Rebel base comes into targeting range. So how does this actually help us determine the mass of Yavin IV? And actually, the targeting display on the Death Star actually helps us. It takes 33 minutes for Yavin IV to go through about 70 degrees of its orbit. And so we now know how fast Yavin IV is going around the gas giant. And if we know how fast Yavin IV is going around the gas giant, and we assume it's on it and the Death Star are on circular orbits, we can use this to figure out how massive Yavin Prime, the gas giant, is. And so the rebels, they have their precious 30 minutes. They go out. We all know the story. They blow up the Death Star at the absolute last possible second. But how massive would Yavin Prime, the gas giant, have to be to give them that time? And is this number even close to reasonable? So I made an assumption. I said we have a large moon orbiting a gas giant, and I figured it probably was somewhere at about the orbit, about the same distance as Ganymede is around Jupiter. So it's making the assumption that in general, planetary moon systems around gas giants would probably be relatively similar, with relatively similar distances. But again, this isn't necessarily a safe assumption, but the only massive gas giant with a large moon system that we have are the ones in our solar system. And when we put all this together, so we put the size of Yavin IV that we calculated, we can measure from this how long it makes it around, makes it around Yavin IV, so we know how fast it's going. And we're making the assumption that it's a moon around a gas giant, so it's probably about as far out as Ganymede. We get that Yavin Prime, the gas giant, is about the mass of Jupiter. And while that's a little massive, it's not completely out of the realm of possibility. So that is basically, so the rebels picked a base orbiting a Jupiter mass gas giant, and the Death Star showed up on the wrong side of the planet. And if you're orbiting that planet, it's going to take you half an hour before you can blow it up. And those are the laws of, that's Newtonian gravity, combination of basic Newtonian gravity and some very simple orbital mechanics. And that's what gave them enough time. But how did we get all this wonderful exoplanet data that I've been comparing the Yavin system to? So we have two options when it comes to detecting exoplanets. And the first one is a stellar wobble or looking at the Doppler. This is talked about stellar wobble. It's mentioned that you're detecting it via Doppler shifts, but they're basically the same thing. And this was how we detected the very first exoplanets. And how this works is that you have, and I'm going to use an iPhone and AirPods to demonstrate this if I can. So you have two systems. You have two stars. It could be a star and a planet. It can be a gas giant and its moon. But anytime you have two things orbiting each other, one object doesn't orbit the other. What they orbit around is a common center of mass. If the two objects are equal mass, the center of mass will be halfway between them. If, like the Earth and the Sun, one object is significantly more massive than the other, the center of mass will actually be very close to the center of the more massive object. So the center of mass of, for instance, the Earth-Sun is actually very, very close to the center of the Sun. But if you have a if you have a massive planet orbiting around its parent star, the center of mass of the planet and the star is going to be ever so slightly outside the star. So the star will actually be rotating around this center of mass. And we detect this as a stellar wobble. The more massive a planet is, the larger this wobble of the star will be. And what happens is, as the star is moving away from us, its light is ever so slightly, the spectral lines in its light are ever so slightly shifted to the red. And then when it moves towards you again, they're ever so slightly shifted to shorter wavelengths, to the blue. And it does this with a very regular pattern. So you see a period. From the length of that period, you know how long it's taking the star to go around the center of mass. From the size of the shift, you can determine the mass of the planet. And coupling all those things together, the first planets that were discovered turned out to be nothing like our solar system. 51 Pegasi b was many times the mass of Jupiter, orbiting inside the orbit of Mercury, something that was inconceivable before the discovery of the first hot Jupiters. We've now found many of them. And it caused us to rethink our model of solar system formation, that our solar system wasn't like every solar system in the galaxy. that they were far more diverse and far more bizarre than we ever could have imagined. But stellar wobble has a problem. It's going to primarily detect massive planets on short periods. So it has a bias. It's not going to give you a fair sample of all the exoplanets out there. So we need another way to go about this. And the other way we go about this is using transits. And many of our transits have been detected by the Kepler spacecraft. And the way transits work is very simple. If any of you saw the transit of Venus, which I know was a long time ago, if you saw the solar eclipse, in 2017, where the moon moved in front of the sun, transits work in effectively the same way. We look out, and there happens to be a planetary system where the planet comes directly between us and the star. And when that happened, the planet blocks a fraction of the light from the star. And so it comes in, it starts blocking the light from the star drops. The length of the transit is the amount of time it takes for the planet to transit across the star. And then as it transits off the face of the star returns to its normal brightness. And from this, you can determine many things, the characteristics of the atmosphere of the exoplanet. And from how long it takes to go into full transit, you can get the object's size. So as it's coming into transit, you begin to drop, and the larger the exoplanet, the longer it will take to go into full eclipse. The advantage of transits is that they're not biased towards only these massive planets close into their stars, and give us a far more representative sample of exoplanets out there. And the better telescope you have, and the more accurate of a light curve you can get during those transits, the better the data and the better the properties of these exoplanets that we can learn. And this is one of the things that's going to be amazing with JWST. So what have we found? There have been 5,000 plus planets found and confirmed. About 30% are gas giants, the size of Saturn or Jupiter. Some of them are big, some of them can be 10, 15 times the mass of Jupiter. Some of these hot Jupiters that are orbiting close into their parent star can even be hotter than the surface of some stars. So hot that their atmospheres are made of metal. About 35% of the planets are Neptune-like, planets about the size of Neptune and Uranus. They can be ice giants, like the outer planets in our solar system, but some of them can actually be warm. Or further into their star, it can actually be warm Neptunes. About 31% of the planets that we found are super Earths. So these are planets that don't exist in our solar system. These are several times the mass of the Earth, somewhere between Earth and Neptune. So this is actually a class of planets that we can't study in our own solar system. We have to study them around other stars. And about 4% are terrestrial. And so what have we found? And the best way to describe this, and when I introduce this to Intro to Astronomy students, I tell them there are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. Or to put this in the parlance of science fiction, whatever weird concoctions humans have come up in their imagination for planets, I promise you the actual universe is weirder. So let's start with some ones that are going to sound somewhat familiar if you're a Star Wars fan. So we're going to start with 55 Cancri E, which is the 55th brightest star in the constellation of Cancer, and the 5th planet, E, around that star. Otherwise colloquially known as the lava planet. This is an artist's impression of 55 Cancri E. The surface of the planet is so hot, but it is a terrestrial world. And the only way that you can explain those two things is if a significant fraction of the planet is covered in lava. So this is an actual lava world that exists in our own galaxy. Then we have Olga 2016 BLG 195LB. This is what happens when you have a very faint star. We don't actually name it. We give it what is colloquially referred to as a phone number. But this is the second object orbiting this. This is the first planet orbiting this star. And it is an ice cold Earth orbiting a tiny star. So it's the mass of the Earth, but it's orbiting so far from its low mass parent star that it's frozen, completely solid. And when this came out, everybody had a lot of fun, basically saying that, have we found Hoth? Which people may remember as the rebel base at the beginning of The Empire Strikes Back. But if you remember on Hoth, even though everybody had to be in winter gear when they were outside, this planet is even less hospitable. Its temperatures are probably closer to those of Pluto in our own solar system. So ice worlds, check, easy, got it. Finally, we have Kepler 16b, which has actually been nicknamed Tatooine. It is a planet that has 2 suns. This is one of the awesome NASA travel posters that have been done for some of the exoplanets. If you want to, they are actually free to download and print off of the NASA website. They're absolutely all spectacular, kind of with an Art Deco look to them. And this is that one for Kepler 16b. So you're on the surface of the planet and you're in the shadow of 2 suns, one of which is a small red dwarf, one of which is more massive and therefore a little more orange yellow. And why is this phenomenal? Why is this strange? In order for a planet to stably orbit a binary system, it likely has to orbit outside of both stars. If a planet's trying to orbit very, very close to one star with the second binary far away. So this is one possibility for a stable configuration for a planet orbiting a binary star. Also, it's a beautiful example of how science fiction, about how astronomy both informs science fiction, but also feeds from science fiction. As Dr. Summers said, as we were sort of prepping for this, pretty much we are generally all nerds. In fact, there has been some joking sort of said that if we find terrestrial planets in the habitable zone, should we call them M-class planets? And now we get to the weird. So those are 3 planets that should seem somewhat familiar to you if you're familiar with the Star Wars universe. And we found things like them. We found a lava planet. We found a planet orbiting a binary star. We found a terrestrial ice world. But then life just gets strange. GJ 1214b is a mini Neptune. So it's a Neptune-like planet, but it's less massive than Neptune. So here's the mass of Neptune. Here's GJ 1214b. And it's covered in water with salt clouds. An entire planet covered in water with salt clouds. GJ 34070b, we have got to come up with better names for these, is actually a rapidly evaporating super Earth. And this gets back to part of that question of why don't we have really warm Neptunes? And the answer is that if you get too close into your star, you get hot. And when you get hot, all that hydrogen and helium in the atmosphere gets hot. And when it gets hot, all those atoms start moving faster and faster and faster. until they're moving so fast they can escape the gravity of the planet. So Neptunes can't be warmer than a certain amount because they'll lose their atmospheres. And this particular planet is orbiting so close to its parent star that its atmosphere is evaporating off. And within a few billion years, half the planet's just going to be gone. We'll have evaporated off into space. Finally, we have TRAPPIST-1. It's a 7 tightly packed rocky planets orbiting an M dwarf. And it showed that if you have 7 planets, you can actually have 7 planets orbiting that tightly together around a star in stable orbits, which we didn't know could happen before TRAPPIST-1. However, because they are orbiting an M dwarf, even though some of them are in the habitable zone, they are also getting irradiated by those solar flares. And so it's unknown whether or not there would actually be life on these worlds. Though, again, based on what we've seen, what we've already found so far out there with exoplanets, I'm not counting it out. So where do we stand? We stand on the cusp of science with JWST. I mean, in a week, we are going to see the first images that come down from it. We know of 5,000 exoplanets with more confirmed constantly. These planets are stranger and more varied than anything science or science fiction has imagined. So if you're watching this and you're thinking about maybe starting playing around with your own science fiction universe, my advice would be go to the Exoplanet Archive, look to see what we've already found, because I promise you it will be stranger, more varied, and more incredible than anything you could dream up. Oh, and the Rebel Alliance had plenty of time to destroy the Death Star thanks to orbital mechanics. And may the Force be with you.
Thank you very much, Mia. May the Force be with you, and also with our online audience putting the questions in the chat. If you have questions for Mia, now's the time to enter them in the chat, and we will ask them of her. But I, as the host, always get the chance to ask the first question. And so somebody was wondering, how do we know Star Wars humanoids breathe oxygen? And if they didn't breathe oxygen, how does this change the analysis? I mean, does it make everything null and void, or is it something that you haven't considered yet here?
Well, I am assuming that. Thanks, Frank. I am assuming for starters, we are always basing, whenever we sort of do science fiction, we always to some extent base it off of ourselves. Particularly science fiction shows, particularly something made in the 1970s and 80s before the advent of modern special effects. So I think it's fair, given that there are humans and they are called humans in Star Wars, that I am assuming that they are biologically similar to humans on Earth. You would still be breathing in some sort of reactive. So all bodies everywhere take in something, use it biologically to do what they need to do, and then expel a waste product. In our case, we breathe in oxygen and we expel CO2. Plants take in CO2 and expel oxygen. So if it isn't O2 that you're looking for, you're still going to be looking for some sort of reactive signature of life that would only be there in our galaxy, because we know that O2, so that's the calculation.
Given the less vegetation on Yavin IV, right? I mean,
I'm assuming they had a relatively high oxygen content.
Unless for some reason processes work differently there.
For some reason, maybe they have reverse photosynthesis or something. But I think we are, again, like we assume also, like I am kind of, they did film that in Tikal.
Yes.
So I happen to know those trees were producing photosynthesis.
All right, so that was one of the weirder questions. There are other questions. Grant, Justice has been following them a little more closely than I have. So Grant, you want to turn on your video and join us and pull out give us the questions that you pulled out of the chat.
And by the way, for anybody who's wondered, yes, I did math to figure out the mass.
So this is actually related to that. Can you expand a little bit more on how you determine the mass of an object by its transit?
So the mass, oftentimes when they do the masses, they do follow up with Doppler. So once we know where the planet is, we can then target that system and do a Doppler measurement. So you can't get a mass from transit. You would have to go back. But a transit, you can just survey the whole sky and look for the dip in brightness. So you can figure out where exoplanets are for a huge number of systems very, very quickly. And whereas getting that Doppler measurement takes a lot more time, you have to actually get the spectra of the star over a chunk of time. So then follow-up is done. So that's why we say there's about 5,000 confirmed exoplanets. We have even more that are candidates that are waiting for that follow-up to confirm that, yes, what's causing that dip in brightness is a planet orbiting the star.
All right.
But again, this is not my area of expertise. So there are.
I always feel sorry.
I mean, it's basics. You know, if you just have the small little thing blocking the light, you know, you get the geometry of the two things. But if you don't know how far away it is, you don't actually have the full orbit for it and such. So you know,
now you can go back and do targeted observations and see the stellar wobble.
Because the Doppler effect relies on gravity, which is dependent upon mass. So one is really dependent upon size, one is really dependent upon mass. Put the two together, you got the full
Density.
information on the system.
Exactly. And what's incredible to me is that we can actually get information on the atmosphere of the system as it moves in and out of transit. Like that to me, I've had people explain to me how it's done, and it still feels a little bit like black magic, because it's just so insane to me that you can get, as it moves into and out of transit, you can actually like get information. You're looking at the star through the atmosphere of the exoplanet, and that just, you know, that's one of those like even astronomer mind blow moments.
I mean, we are looking at the atmosphere of a planet that we can't see.
Yeah,
we can
exactly.
see, we can detect what's in its atmosphere, but we can't actually see it.
Yeah, like how we determine how we find life for the first time in the universe is not going to be ET phone home. It's going to be, oh my God, we have a clear oxygen 2 signature in an exoplanet atmosphere. And then you're going to watch like all of astrophysics go completely insane.
Okay. All right. But you know, one of our viewers actually, sorry, brought up that oxygen can also be produced abiotically. So, I mean, on Yavin IV, there was so much vegetation. Of course, the oxygen had to be produced from the vegetation. If you saw it, it would be produced by vegetation. But could we, I don't know, I'm not an expert in this either. Are there abiotic processes that could produce enough oxygen that you could get that signature in an atmosphere?
I don't know. My memory from when I learned about this, when I remember learning about this, when people sort of were talking about it, was no. That it's not as strong of a signal, and that if you want to get really high amounts of it, there isn't a known abiotic process that could produce sort of that amount, but don't quote me on that.
Okay, well, you know, we're just speculating here, one non-expert to another, but that was somewhat my memory as well, that you could produce a certain amount, but the depth of the oxygen signature in the spectrum would be an important factor in terms of whether or not it could definitely be could be abiotic or had to be due to biology.
And there's the question of how deep would it need to be to even see it, because remember, you were looking at the atmosphere of an exoplanet as it goes into transit.
Yes.
I'm sorry, my mind, that's still like every time I hear somebody talk about it, I just go like, I know, I understand everything you're saying. I see your logical progression. This feels like black magic.
Someone in the comments
extent.
actually said exactly that, black magic. So
Yeah, it feels like, and even for us, the non-experts who don't do exoplanet atmospheres, it's like,
we've had someone on here explain it, and it's still, yeah. All right. If the gas giant is anything like Jupiter with its massive magnetic field, wouldn't the radiation belts be a negative factor in a viable moon unless it itself had a massive magnetic field?
well, the magnetic fields, that's actually a very good question. Jupiter's moons actually orbit, I believe, inside of Jupiter's magnetosphere. Jupiter's magnetosphere is absolutely massive, and I'm going to see if I can find a diagram of it, because
my recollection from my graduate school days, which was probably about the time you were being born.
Yeah, we're not discussing that, and yet can we like, we're not discussing the fact that people are sitting on Hubble tax who weren't born when it launched. Yeah, we're
the magnetic field of Jupiter is larger than the sun.
Yeah, it's absolutely. I'm seeing if I can find a diagram that shows it.
And well, I was
because like Google knows basically what, generally speaking, Google knows all, or at least you can find everything you need on Google.
I was at Berkeley, and Imke de Pater was a Jupiter expert there, and she did a lot of observations.
I remember it being bigger than, like, however big you think it is, it's bigger. And it encapsulates.
But the question is important, right? I mean, if you've got the at least in Jupiter, you've got the kilometric radiation that's bouncing up, the charged particles that are bouncing from the top to the bottom and top to the bottom, et cetera. Now, if a planet is flying through that and it doesn't have its own,
magnetic field
to stop it, that could cause some problems.
That could cause issues. I think, I mean, that was part of the reason why I made the assumption that Yavin IV is at Ganymede, because the assumption would be that it would then be inside of the magnetosphere of the planet. Now, what this would do to the electronic systems on the Death Star is a completely other question. We're assuming that maybe they did really good shielding on it, because
I mean, one good cosmic ray hit can take out a Death Star.
Yeah.
We're also talking about the same people who didn't put safety rails on the giant chasms in the middle of the Death Star.
That too, right. OSHA would have a field day with this.
We now know why the thing blew up, but that's neither here nor there. But I mean, that's actually, if you think about the size of the magnetic field of Yavin Prime, it does actually. The more interesting question is actually why was the Death Star still functional?
Much less able to condense a beam and then send it out to destroy. Yeah.
Given how much, for just for the record, when NASA sent the space probe into Juno, this was a real issue. It was designed to survive the interaction with the magnetic field, and there's shielding on it that does this. So just, I guess, assume that the Death Star has a lot of shielding. Okay.
So, but important props to the question, the person asking the question, that, magnetic fields, in astronomy, we say if we can't explain it, then we just invoke magnetic fields, right? Here is one where we don't want to try to invoke magnetic fields, because they would definitely confuse the system. Go ahead.
No, I was just going to say that's also the question you ask at the end of a colloquium if you haven't been paying attention.
Yes.
What about the magnetic fields?
Go ahead, Grant. What's next?
We had someone in chat actually answer the question. 5.3 million kilometers, 3.3 million miles wide on average, the magnetosphere. 150 times wider than Jupiter itself, and 15 times wider than the sun.
So I think it's safe to say that Ganymede is inside of that.
Yeah. So, the question is, at what radius would the radiation running up and down the magnetic fields be important? Because it's not going to be all the way out, and it's not going to be all the way in. So
there's going to be some point where your the magnetic field itself is causing more damage than the shield that it's providing from the solar wind.
Okay.
All right. So
and now I'm going to
follow
go
up
look
to
this up.
This is you'll add it to the next time you give this talk, right?
Speaking of atmospheres, why does Venus have a thick atmosphere even when it's so close to the sun? Why hasn't it escaped into space like the Mars atmosphere?
Venus's atmosphere, well, I mean, I knew somebody was going to ask me about Venus. Well, for one thing, Venus is about the mass of the Earth. It's a little less than the mass of the Earth, but people call it Earth's twin. It's about the mass of the Earth. Mars is actually significantly less massive than the Earth. And the reason what lost Mars its atmosphere is because it was less massive, it cooled and it lost its magnetic field. And without the magnetic field, you have the particles of the solar wind, they hit the atmosphere, you begin to break apart the molecules that are in the atmosphere. And once those molecules are broken apart and they're lighter, they are moving faster and then they escape and Mars's atmosphere effectively evaporates. So that's what happened to Mars. Venus, the atmosphere of Venus is actually made, and Frank, you can help me a bit on this. It's sulfur. Is it sulfur dioxide?
Yeah.
It's very
it's
heavy
carbon
molecule.
dioxide. I think
It's carbon dioxide.
I thought it was 90
and
something
sulfur.
percent carbon dioxide.
90 something percent carbon with sulfur. So these are not, there's actually not a lot of water, interestingly, in Venus's atmosphere. There is also no magnetic field in Venus because Venus is orbiting so slowly that it can't actually maintain a magnetic field. So basically you have these heavy particles in the atmosphere, and the heavier the particle is, the same amount of energy will mean that it moves slower. So those heavy molecules aren't going to be able to go fast enough to actually sort of evaporate off. Whereas hydrogen, lighter things like hydrogen are just going to go like, see you later, and they're going to be gone if you're not being protected by a magnetic field. So Venus is actually dry.
Yeah, the thing I remember about Venus is that it's got so much carbon dioxide in its atmosphere. But if you look at like the limestone, the calcium carbonate at the bottom of our oceans, if you heated up Earth such that you got rid of the oceans and all that calcium carbonate turned into carbon dioxide, we'd have just as thick atmosphere as Venus. Yeah.
Except
so
we have a carbon cycle.
Yes, and
So,
we're a little further away, so we get better.
Further away, so Venus is like just inside the habitable zone, and we're dead in the middle of the habitable zone. So we've got that going for us. But we also have a species that is dumping carbon into the atmosphere at an unprecedented rate, and that,
Yeah, Wikipedia says it's 96.5% carbon dioxide.
Carbon dioxide.
Yeah.
Basically, don't go to a vacation on Venus. It's not a good spot.
Short-lived vacation.
Very short-lived vacation.
Well,
how long did the Soviet lander make it? Was it like
the Venera probe, landed, got some pictures, and then it melted.
Yeah. The surface of Venus is hot enough to melt lead.
There you go.
That would do it.
Yeah.
Okay. So
wait a minute. I'm going to jump in here for a question here because there was one thing that sort of thing. All right. So you're talking about Yavin Prime being the gas giant.
Yavin Prime. Now this I had to look up on Wikipedia, and yes, it's a thing.
Yes.
Yavin IV is the moon.
Yes. That
Yavin
I understood.
Prime is the gas giant.
Okay. So Yavin Prime is a gas giant that's supposedly orbiting in the habitable zone.
Orbiting in the habitable zone of probably a relatively sun-like star.
Relatively sun-like star. Okay. So do we have observations from Kepler or other places that give us gas giants in a habitable zone around such a star? I mean, have we actually seen something like this?
I remember.
You talked about the moons that we've seen, and that we've got a Hoth and we've got a Tatooine, I think. Do we actually have a Yavin Prime?
A Yavin Prime. I remember there being a big deal, and this was when I was a wee little thing.
Okay.
That there is a really big news article. Virginis, I think, was the constellation that they had found a gas giant that was in the habitable zone. This is back when they were just using the Doppler shift. So it was all massive planets close in. And so I remember, I think I have the clipping from the Washington Post in a note, taped in a notebook, that it was this big deal that they found a gas giant in the habitable zone. I don't want to say definitely yes, but it would shock me if somewhere in that like 5,000 planets that we haven't found a gas giant in the habitable zone. The other moment that all of sci-fi fans went completely nuts for planets is when we found something around Proxima Centauri, because in about 3 different sci-fi universes, there's a colony at Proxima Centauri. So that proceeded to have all of us go like, you know,
it's possible.
It's possible. Oh my God.
Well, I mean, for me, finding something around Proxima is like, you know, all right, there can be planets around red dwarfs, and red dwarfs are the most numerous
common
types of stars out there. So if you don't have planets around there, you're lacking for planets in the universe.
Yeah, exactly.
Yeah,
for me, the other
you can
big
have
one
planets
was,
around red dwarfs.
They found a planet around a star that was in like I think like a 10 billion year old cluster, so like around a really old star, and that resulted in extensive amounts of in case anyone noticed, I'm a complete sci-fi nerd, it resulted in extensive Babylon 5 references that we'd found Zahadum. So for people that sort of really wonder, like, it really is true that like sci-fi, we feed sci-fi, so they're pulling stuff, the Hubble images have been used as backgrounds for how many space shows over the last 30 years.
Yeah, I mean, it's actually poor advertising for the web space also, because Star Trek is always using Hubble images, so in the 24th century, web doesn't get any play, does it?
Yeah, it doesn't. But the thing is, like, what you have to realize is that this is also, we're also being run by a bunch of nerds. So we nickname planets Hoth and Tatooine because that's shorthand for us. And I think somebody at some point, and I don't think it was entirely a joke, suggested naming terrestrial planets in the habitable zone M-class planets. Like, we're nerds, but it also helps from a public facing perspective because it's shorthand.
Yeah.
A lot of people know if they hear M-class planet, they are at least sort of aware of what that means. And so that's a nice shorthand for how important a terrestrial planet in the habitable zone of a star would be.
Okay. All right, Grant, what else we got?
I like this question, but it is not necessarily astronomy related. Why couldn't the Death Star just shoot through the atmosphere of the gas giant to hit the rebel base? But then that's talking about the power of the Death Star and what
it's talking about
penetrate.
The power of the laser and the fact that
like
initially they were shooting through more than just the atmosphere. You would have had to shoot through like the whole planet, and
that's all based on theoretical
and this
things
is of course assuming
George
that
Lucas
it didn't
came up with.
Yeah, and this is also assuming, this is also assuming that it didn't get fried when it went through the magnetic field of Yavin IV. So
true. All right, so why haven't we been able to determine if Kepler 452b has oxygen in its atmosphere? And if that's too specific, what kind of things do you need to go through in order to determine something like that having?
It's not that strong of an absorption line. So you need an incredibly powerful, you basically need a better telescope. Cue JWST. you basically need a better, it sounds flippant, but it's really not. It's not a strong line. It's not the strongest absorption line that you're going to see in an atmosphere.
Mia, do you want to say something about spectra and the resolution of spectra and the different spectrographs and how that has evolved over years?
Okay, so you've got 2 problems that you're dealing with. First off is the amount of glass. They're literally the size of your primary mirror. JWST is 6.5 meters across. I think one of the hexagonal segments it's 18 hexagonal segments, and one of those segments, am I right, is about the size of the Kepler mirror? Order of magnitude.
It's certainly one of them is certainly larger than the Spitzer mirror, right?
Than the Spitzer mirror. So this is the biggest thing we've ever pointed at exoplanet atmospheres, like ever. So that's the first thing, is that the telescope can collect a lot more light a lot faster. The second thing is that when we observe with spectra, the resolution of the spectra is how finely in wavelength can we determine a line. So that if you have a spectrograph that's low resolution, you might have a line sitting here, but if you have another stronger line that's right here, they're going to get completely, we call it actually blended together, and you're just going to see the one line that corresponds to the stronger line. So oxygen 2, because it's a relatively weak line, you need both a lot of glass, you need a lot of light hitting your mirror very quickly, but you also need high resolution spectra so that you can differentiate, okay, here's oxygen, right, from all the other lines that are right near it and that may be stronger. And so over time, our spectra have become higher and higher resolution. So they've been able to resolve out lines that are very, very close together. So what it looked like one line, we can now see is actually two lines. And I don't know what I'm allowed to say about, yeah, that I'll wait for, I don't want to say something because I don't know like what's public
don't do
and
that.
what's not.
Yeah.
So
I don't even know what, yes. But the other point is that, you know, for our audience is that Kepler was designed to just measure light curves, right? And so Kepler didn't do any spectra. It just measured light curves, you know, the brightness of a couple 100,000 stars over and over and over and over and over and over and over again. So it got the light curves that went and found the dips and everything. In order to get the spectra and look at the atmospheres, you have to do follow-up observations, but most of the Kepler stars are too far away for really good follow-up. Okay, they aren't going to produce enough light. You aren't going to be able to get enough photons to be able to get a good spectrum of it. So the mission that actually is that's sampling the exoplanets that we will be able to do follow-up with Webb is the TESS mission. So unfortunately, Kepler 452b or whatever 462b, I can't remember its number. Is a great understanding, and we can figure out, we can understand the solar system, but the follow-up observations, my understanding is it's too far out there for us to get really good follow-up observations.
And you've got this additional thing that the O2, when I'm looking at sort of where the O2 line is located, it's located, I believe, in the near infrared.
Yeah.
So, and in the near infrared, when we're dealing with our atmosphere, we actually have sections of the atmosphere because of the water vapor in our atmosphere that we can't see.
Yeah.
So we had to really do near infrared really, really well. We have to go to space.
Yep.
Which is also, you know, why we have a brand new telescope at
L2. We'll talk about that next month.
Yeah, that'll be when I was deciding on topics, it was this or first light, like when we talk about first light with JWST, what do we mean? And my former boss, when I was here, said they're going to be hearing so much about JWST for the next year, talk about Star Wars.
Yes, I agree. I thought that was a fine thing. You know, you can't be, you can't compete with the real thing. All right, Grant, any more questions?
Yeah.
Okay.
First off, I want to head this off at the pass because it's going to get asked if it hasn't already. Resolution is a term that people hear a lot, but it's usually related to video outputs. When you talk about resolution in spectra, what do you mean?
So when we talk about resolution in spectra, what we mean is how well we are able to differentiate two spectral lines. So if two spectral lines are very, very close to each other, you need very high resolution to differentiate between them. So it's like, can you differentiate between two lines that are 10 nanometers apart versus 2 nanometers? So a higher resolution spectra is going to be able to differentiate between lines that are 2 nanometers apart rather than, 10 nanometers. And there's always a trade-off between the resolution and your wavelength coverage.
Yep.
So how much of the spectrum can you do? So oftentimes instruments will have one sort of lower resolution spectrograph that covers a wider wavelength range, so a wider range that you can, if you don't need that really high resolution, you can just use that. And then they'll have a really high resolution spectrograph that has a narrower wavelength range for when you really, really need that incredibly sort of different, you need the differentiation between those really, really fine lines. And high resolution spectroscopy Is it fair to say that that is one of the hardest things as far as amount of photons and amount of light you have to bring in? It's one of the most difficult things that is done in astronomy is high resolution.
So, I mean, imaging, you're
spectroscopy.
just taking all the light and you're seeing the intensity of the light. Spectroscopy, you're taking that intensity of light and then trying to spread that out and trying to get the intensity in there.
And the more
And
finely you spread that out, the lower your intensity is. And so high resolution spectroscopy is often really high resolution spectroscopy has to be done in very large telescopes with some of the most sophisticated instruments that we have.
You need lots of photons to do
Lots of photons.
high-res spectra.
Lots
If
and
only
lots.
we
You
had
need
a
a
new
very big
telescope.
photon bucket.
Okay. All right.
What sort of things do you look at? Like what kind of spectral lines would show, or would you look for a habitable planet or existence of, like, if you were looking for life or you were looking for the right conditions to show life, what kind of spectra would you look for?
I would say water, actual water lines in the atmosphere would be one for me. But again, I'm not an expert in this, whatsoever. I mean, the first pass is it in the habitable zone? And is it a terrestrial planet? Because we are not going to be able to figure out what's going on a moon around a gas giant anytime soon. So it really needs to be a terrestrial world, so a world that is high density in the habitable zone of a star. That's like cut one. And then you try to look for signatures, like oxygen's the big one, O2. But there's other signatures as well. If I saw water vapor in the atmosphere, like a lot of water vapor in the atmosphere, I would assume that you maybe had a water cycle going on that planet, that you had a magnetic field that was protecting it. Because if you don't have a magnetic field that's protecting it, the solar wind can come in and sort of dissociate, break apart the water molecules, and then the hydrogen's going to go see you later off into space. So those would be some of the ones I think of. I don't know if you've got any that.
What I would start to look for is I would look at the Earth's what we do when we discuss this generally is we look at Earth's atmosphere. What are the signatures that we see in Earth's atmosphere? Not all of those can be directly tied to biology, but similar like that. I mean, I think what's going to happen, which is going to be fantastic over the next 30, 50 years, is that we're going to suddenly develop this family of, as we've developed a family of planets out there, right? And they've exceeded our expectations, right?
They blow our minds on a monthly basis.
We're going to develop a family of exoplanet atmosphere characteristics that's going to challenge us to explain, well, what the bloody blazes is going on here.
And and that is the ragged edge. Exoplanet atmospheres. I mean, when I emailed Tad to get the information for the color of Yavin Prime, I figured, oh, there's got to be a paper out there. Somebody has to have done this. The answer turned out to kind of be no. And he's like, well, this is what my intuition is telling me, but this isn't really something that anybody's been able to do. So it's when we're talking about these observations of exoplanet atmospheres, it isn't pie in the sky, but it is a longer term thing. This is 10, 15, 20 years.
Look, we didn't have other planets 30 years ago, okay? 30 years ago.
We didn't have other planets 20 years ago.
We're talking 30 years ago, 1992, which is 30 years ago.
Oh God, that was 30 years.
It is 30 years, okay? You can feel old too, Mia. 30 years ago, we didn't know of any other planets. Now we have all these other planets, and we're starting to understand atmospheres. 30 years from now, which is one of the reasons I said that, was we'll have a whole lot of atmospheres, and we'll still be confused by it because nature is more inventive than our imaginations.
Yeah. It's if anybody's ever played the video game Mass Effect, one of the professors at Maryland once commented that the exoplanets were weirder than the Mass Effect planets.
Nature is always stranger than the imagination.
Nature's always stranger than fiction. That's why I love that. When I was looking for a quote to start up the discussion of the planets, I was just like, oh, this is perfect.
Okay.
There are more things on heaven and earth.
All right, so I think we're going to leave it there because we're approaching an hour and a half. And I will put it into one final question for you, Mia, which is not on this topic, but is on next week's topic. What is it that you are most excited about or most anticipating with the Webb Space Telescope?
The thing
As
we
in
don't,
effect, yeah.
the thing we don't expect to see. There are things that we're pretty sure we're going to see. Every galaxy that Hubble can see, January's taking it a spectrum. And so there are a lot of things that we know that we're going to see, that we're kind of expecting, right? We know when we look deep in an extragalactic field that we're going to see more galaxies, that we're going to see galaxies further back. Like, we know this, right? But there's going to be something. And I think it's going to be in every field. It's going to be in exoplanets. It's going to be in stellar. It's going to be in nearby galaxies. It's going to be in distant galaxies. There's going to be something that just changes the paradigm, changes the conversation that we absolutely didn't expect. And that's the thing I'm really excited about. Now, that doesn't mean I'm not going to drool over the pretty pictures that we're getting next week, but it's the thing that we didn't expect. It's the unknown.
I mean, it's kind of like for Hubble, the image you have behind you of these deep fields of galaxies, right? We did not know we were going to get that with Hubble, right? Matter of fact, it was quite a risk to put that much time into doing a deep field.
And it was director's discretionary, correct?
It was director's discretionary time. This was Bob Williams saying, I'm going to throw 300 orbits at one image. And basically, if it fails, yeah, I'm fired.
I'm going to go point the most powerful telescope we have for 300 orbits. For those of you that are listening, that is an insane amount of Hubble time, like crazy, like ridiculous. And if anybody had proposed to go through the allocation committee to point Hubble for 300 hours at nothing for 300 orbits, they would have been laughed out of the room. And yet he said, with his director's discretionary, which is time that the director of Space Telescope can choose to use as they see fit, he then said, I'm going to point this at nothing and I'm going to see what I see. Now, the one behind me is the ultra deep field, which was the second one that was done, but the original deep field
was a risk. Yeah.
It was a risk, and they didn't know this. It was an empty section of sky. I think it's what the size of a dime, the eye on a dime or something, at arm's length, and there was nothing there. They knew they purposely picked something, but there was nothing there, and they could have gone out and they could have seen nothing, and it could have been a complete dud. And instead, we got a field of not of stars but of galaxies, where every single point of light behind me is a galaxy.
So I just use that as a point for our audience that, you know, we didn't expect that from Hubble, and there'll be things we don't expect from Webb, and they're going to make Mia happy.
They're going to make, honestly, that's what a lot of
everyone happy.
I think that's what we're all the most excited about. It's like the stuff we're expecting. We're like, yeah, that's great. It's going to be nice science. It's the stuff it's what's the phrase of scientific discovery? The most important moments in science are not heralded with eureka, but what? You know,
I think that's a great way to end it. Okay. All right. So next month, well, first of all, next week, July 12th, watch the NASA broadcast and see the new images and spectra from the Space Telescope, the Webb Space Telescope. And then on August 2nd, Alex Lockwood will explain it all to you. She'll have all the answers, and she probably won't have that one thing we don't expect yet, but she will do a fantastic job of explaining. So thank you all and have a great day.
Have fun next week, everybody.